Carboxylic acids possess a poor leaving group on the carbonyl carbon. This makes them largely unreactive in nucleophilic acyl substitution, which is the predominant reaction of carboxylic acid derivatives. Consequently, it is useful to be able to convert carboxylic acids to acid chlorides, which are much more reactive in nucleophilic acyl substitution. And this is accomplished by treatment with thionyl chloride. The mechanism begins with the attack of the carboxylic acid on the electrophilic sulfur of thionyl chloride. As it does so, the carboxylic acid also sheds a proton to the medium so as to remain neutral. The sulfur-oxygen pi bond is displaced onto oxygen as a lone pair of electrons. This happens as a result of sulfur acquiring a new bond to oxygen. In the next mechanistic step, the sulfur-oxygen pi bond is reformed as chloride dissociates. The net result of the mechanism thus far has been to convert a poor leaving group, the hydroxyl group, into what is a much better leaving group. With a good leaving group now bonded to the carbonyl carbon, the substrate can undergo nucleophilic acyl substitution. And the general paradigm for nucleophilic acyl substitution is that a nucleophile attacks the carbonyl, a tetrahedral intermediate is formed, and as that intermediate collapses to reform the carbonyl, a leaving group is lost from the carbonyl carbon. In this specific nucleophilic acyl substitution, chloride attacks the carbonyl carbon, and as it does so, it pushes the pi bonding electrons onto oxygen to form a tetrahedral intermediate. The tetrahedral intermediate is named as such because the reactive carbon began as a carbonyl carbon. It was sp2 hybridized and therefore trigonal planar or flat. But upon addition of chloride, it became an sp3 hybridized center, which has tetrahedral geometry. Hence the tetrahedral portion of the name tetrahedral intermediate. The reason it's called a tetrahedral intermediate is because that tetrahedral geometry will be lost as the mechanism moves forward. In other words, in the final mechanistic step, the carbonyl pi bond is reformed as the leaving group dissociates. Now, this particular leaving group is somewhat unusual in that it fragments as it dissociates. In other words, the electrons from the breaking carbon-oxygen bond form a sulfur-oxygen pi bond, and as they do so, chloride is displaced. The net result is the acid chloride product of interest, as well as byproducts including sulfur dioxide and chloride. The fragmentation of the tetrahedral intermediate into 3 pieces during the last mechanistic step is entropically favored. These 3 species increase the disorder of the system. Additionally, sulfur dioxide bubbles out of the reaction mixture, thereby helping to drive the reaction to completion. In the following specific example, benzoic acid is converted to benzoyl chloride by reaction with thionyl chloride. The transformation begins with the attack of benzoic acid on the electrophilic sulfur of thionyl chloride. A proton is lost during the process so that a new carbonyl can be formed, thereby maintaining the desired valence at the carbonyl carbon. Finally, the sulfur-oxygen pi bonding electrons are pushed onto oxygen as a lone pair. This anion then collapses to reform the sulfur-oxygen pi bond. As that occurs, chloride is pushed off of the substrate as a leaving group. The carbonyl carbon now bears a good leaving group that can be replaced by chloride as the mechanism progresses. This process begins with the attack of chloride on the carbonyl carbon, and this attack results in the carbonyl pi bonding electrons being displaced onto oxygen. A tetrahedral intermediate is formed. In the last mechanistic step, the anion of the tetrahedral intermediate collapses to reform the carbonyl pi bond. As this occurs, the leaving group dissociates with the formation of sulfur dioxide and the ultimate displacement of chloride. The net result is the generation of benzoyl chloride as our product of interest. In summary, carboxylic acids can be converted to acid halides through exposure to thionyl chloride, and the mechanism involves two stages. In the first stage, the hydroxyl group is transformed into a good leaving group. And in the second stage, this good leaving group is replaced by chloride through nucleophilic acyl substitution. The significance of this reaction is that it converts a poor leaving group on the carbonyl carbon into a good leaving group on the carbonyl carbon. And this opens the door to many subsequent reactions. The importance of this will be underscored as we move into the next video on the nucleophilic acyl substitution of acid chlorides. The preceding was an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, or in paperback at a discounted price from Lulu.